Welcome back to the deep dive. Today we're grabbing what I think is a real shortcut into understanding the economic forces shaping our ocean's future.
Yeah, we're digging into a pretty important paper.
We are. It's Why Economics Matters for Understanding the Effects of Climate Change on Fisheries by Alan C. Haynie and Lisa Pfeiffer from back in 2012.
And our mission today is really to get under the hood of this thing, to understand why so many predictions about where fish will go, with climate change,
Yeah.
why they often miss a huge variable.
The human variable, right? The people actually catching the fish.
Exactly. That's the core issue the paper hits head on.
Yeah.
A lot of the traditional predictions, they sort of oversimplify things, don't they?
They really do. The general idea being that the future of a fishery is just dictated by where the fish decide to swim.
Right.
Okay, let's unpack this. So the prevailing, almost kind of basic prediction is just fisheries follow fish. Cod move north, boats move north. Simple.
Too simple.
But Haynie and Pfeiffer, they were arguing almost a decade ago that this ignores this massive, complex economic engine humming away beneath the surface.
Precisely. We really need to stop looking at fisheries as purely biological puzzles. Climate effects involve physics, biology, and economics, all interacting.
And if you only model the first two?
Your long-term predictions, well, they're likely to fall apart. The key insight really is that harvesters aren't static. They react dynamically.
To what? Changes in the market, rules, the environment itself?
All of the above. Economic conditions, institutional rules like quotas, environmental shifts. And those responses are what actually determine where the fishing effort ends up.
And this isn't just academic. We're talking about real-world consequences. Policymakers, fishing communities, they have billions riding on getting these predictions right.
Absolutely. They need to know how fishing patterns might shift spatially, temporally, which species get targeted.
And which communities might suddenly find themselves struggling if the boats go elsewhere. It's about vulnerability, too.
Definitely. So to give reliable answers, you absolutely have to understand what drives the fleet's decisions.
So how do they break that down? What are the main drivers?
Well, based on the paper, you can think of it in roughly three categories. First, you've got factors directly tied to biology.
Like how many fish are allowed to be caught? The tack? Or just, are the fish even there?
Exactly. Total allowable catch, spatial distribution, abundance, basic stuff.
Okay.
Then, category two, factors that are influenced by biology but kind of filter through economics.
Give me an example of that.
Okay, so the paper mentions how changing ocean temperatures might not just move the fish, but could change, say, the timing of spawning. Which could separate the larger high-value females from smaller, less valuable fish.
Yeah.
So the value of fishing in a certain spot changes dramatically, even if the total biomass hasn't shifted much.
Got it. So it's not just where the fish are, but what kind of fish and what they're worth.
Precisely. And then the third bucket, which is maybe the most critical and often overlooked, external factors. Things completely separate from the ecosystem.
Okay, like what?
Think fuel prices, labor costs, a sudden craze for a specific processed fish product boosting demand, or even, politics, a trade dispute that shuts down a key market.
Right. And ignoring how climate interacts with all of those,
Yeah.
you're missing a huge piece of the puzzle.
You really are. So if the why is that harvesters and their choices are central, the next big question is how? How do you model that complexity without it just becoming chaos?
That's the challenge.
And what's fascinating here is how the authors use this conceptual framework. It's a way to impose some order, to push researchers beyond just seeing correlations.
Towards causality, like what actually causes what?
Yeah, exactly. Their figure one, it maps out the mechanisms. It links environmental factors, maybe Arctic oscillations, sea ice, temperature, to the biological changes.
Recruitment, survival, where the fish hang out.
Right. And then crucially, links those to the economic factors that ultimately drive where the boats actually go, where the fishing effort is distributed.
It's like a roadmap for thinking through the connections designed to stop people making lazy assumptions.
Spot on. And it forces us to think about timing, too. They distinguish between solid lines, immediate effects, and dotted lines.
What do the dotted lines represent?
Those are non-contemporaneous or lagged effects. Like, heavy fishing now might only impact fish recruitment, the number of young fish entering the fishery several years down the line.
So there's a delay. That's crucial for management.
It's huge. It means a decision based on today's data might not show its full impact, good or bad, for years. Ignoring those lags is a classic way predictions go wrong.
Okay, so let's get to the economic model itself. What's the foundation?
Well, it starts from a pretty standard place in economics. The individual harvester is trying to maximize their utility.
which for a commercial fishing operation usually boils down to maximizing profit, right?
Generally, yes. That's the simplifying assumption often used. That's the engine driving their choices.
So how does the model capture that decision? What goes into it?
The paper outlines a basic location choice model. It focuses on maximizing expected profit. 3 key variables pop out.
Okay, what are they?
First, expected catch quantity. How many fish do I think I'll catch there? Let's call it EQ.
Right, volume.
Second, expected unit value or price. What do I think each fish or ton of fish will be worth? E price.
Makes sense. Value.
And third, the cost of fishing. This is dominated by travel costs, fuel, time getting to and from the fishing ground.
So if I'm the captain, I'm doing a quick mental calculation. Which spot gives me the best combination of expected catch and expected price minus the cost of getting there?
That's the core idea. If the expected price goes up, or the chance of a good catch goes up, I'm more willing to spend more on fuel to travel further.
But hang on, it can't be that simple. Captains aren't just optimizing machines. What about rules and regulations? Don't they constrain these choices?
Yes. That throws a massive wrench into the simple profit equation. You're right. The management system is critical.
How so?
It fundamentally changes the incentives, the trade-offs a harvester faces.
Okay.
Think about the 2 main types of management they discuss. First, a non-rationalized fishery. This is where there's a total quota for everyone, first come, first served.
The classic race for fish.
Exactly. The incentive there is volume, volume, volume. Maximize your catch, your queue, as fast as possible before the whole thing closes. You might burn excessive fuel, take risks.
Because speed and quantity beat careful targeting or maximizing value per fish.
Right. But contrast that with a rationalized fishery, think catch shares or individual fishing quotas and IFQs.
Where each boat or operator owns a specific share of the total allowable catch.
Correct. Now the incentive flips. You own your share, you can fish it whenever you want during the season. The race is off.
So you can slow down.
Yeah.
Be more strategic.
Precisely. You can focus on maximizing the profit from your quota over the whole season. Maybe that means fishing less today to wait for better prices tomorrow. Or targeting areas with fewer fish, but much higher value per fish.
Okay, that makes sense. The rules totally change the economic game.
And the Alaska pollock example they use in the paper, it just perfectly illustrates this power of value over volume, especially under certain management systems.
What did they find there in the Bering Sea?
They looked at the eastern Bering Sea pollock fishery and found that the value per ton of pollock caught wasn't the same everywhere. It varied significantly by location.
How so? Which areas were better?
The southern regions were consistently higher value per ton, significantly so.
Why? Were the fish bigger there or just better quality?
It was something quite specific and seasonal. Roe.
Fish eggs.
Yep. There was a spatial price premium specifically because of the high-value roe harvested from pre-spawning female pollock, which congregated in that southern region during the winter.
Wow. So it wasn't just the fish meat itself.
Not primarily. This roe could fetch a 50 to 200% bonus on top of the regular price for the fish. That's a massive incentive.
Okay, wait. Let me get this straight. A temporary seasonal thing, like where the fish are spawning and maturing their roe, that can be a more powerful driver of where the boats go than just the overall density of fish.
That's exactly what they found. That's the key discovery. Harvesters were willing to travel further, maybe even catch slightly less volume sometimes, to hit those southern areas during winter because the value is so much higher.
The implication seems pretty stark then.
It is. If your model only looks at catch per unit effort CPUE, basically how many fish you catch for the time spent fishing, and ignores these spatial and temporal differences in value.
Your predictions about where fishing effort will go are going to be seriously wrong.
Dead wrong. Harvesters aren't just chasing fish density, they're chasing the highest concentration of money.
Which brings us back to those external factors too, right?
We have to remember them. Imagine a big spike in fuel prices happens at the same time as a minor climate-driven shift in where the fish are. The change you observe in fishing effort might look like it's all about the fish moving, but it could be mostly driven by the increased cost of travel due to fuel.
So you could easily misattribute the cause entirely to climate change, when really it was the gas pump.
Leading to potentially bad policy decisions based on a faulty understanding.
Okay, so here's where it gets, I think, really interesting. We usually think climate impacts economics through biology, right? Warmer water, fish move, so economics changes.
That's the standard pathway.
But the paper points out that environmental factors can hit the economics directly bypassing the biology step initially.
Right. Give us the prime example they use for that.
Think about a high-latitude fishery, somewhere with seasonal ice cover.
Okay.
If you get a decrease in winter ice cover due to warming, that doesn't necessarily change the fish biology overnight.
True, the fish might still be in the same general area.
But it immediately changes the economics. It lowers the cost and risk of fishing in those areas, and it might open up waters that were previously completely inaccessible during winter.
Ah, so it directly affects the expected profit calculation by reducing costs or opening new opportunities.
Exactly. The distribution of fishing effort can change instantly, purely because the physical environmental change affecting access and cost, even before any major biological shift happens.
That's a crucial direct link. But the real headache for researchers comes when multiple effects happen at once, when they're compounded.
Yeah, that sounds messy.
It is. You might have that decrease in ice cover, which lowers travel costs, happening at the same time as an increase in water temperature.
Which might affect, say, that roe maturation timing and the expected value.
Right. So both things are pushing the fleet towards a certain area, maybe for different reasons, one cost-related, one value-related, but they happen together.
So how do you separate them? How do you know which factor is doing how much of the work in shifting the fishing effort?
It's incredibly challenging. Their effects are confounded. You see the boats move, but pinpointing the exact contribution of the ice versus the temperature versus maybe a simultaneous change in fish abundance becomes really, really hard.
And these effects could even cancel each other out, right? Masking changes.
Absolutely. Imagine the fish stocks do shift further away from port due to climate change. That should increase travel costs and maybe reduce effort in that area.
Okay.
But what if that happens at the exact same time as a major global collapse in fuel prices?
Ah, so the increased distance is offset by cheaper travel.
Precisely. The expected change in fishing effort, the reduction you'd predict from the fish moving, might completely disappear in the actual data. It gets masked.
And if you're only tracking the fish location data, you'd conclude wrongly that the shift didn't really impact the fishery's economics or behavior.
You'd miss the crucial economic counterforce entirely, which leads us straight into the limitations and the inherent uncertainty here.
Yeah, the paper cites other work, doesn't it? Saying human behavior is basically the biggest wild card in managing fisheries.
It does. Fulton Dell, at 2011. Human behavior is flagged as a key source, maybe the key source, of uncertainty.
And when you start layering models,
Yeah.
it gets worse, not better.
That's the uncomfortable truth. You take your already uncertain biological models, predicting fish stocks is hard. And then you add uncertain economic models on top.
Trying to forecast things like fuel prices or consumer tastes or even political stability 10, 20 years out, good luck with that.
Exactly. These are notoriously volatile. So when you combine these uncertain economic forecasts with uncertain biological forecasts, the total uncertainty in your long-term prediction doesn't shrink.
It compounds, multiplies.
Potentially, yes.
Yeah.
The uncertainty balloons. It's not like the errors cancel out nicely.
So the complexity feeds the uncertainty. It's like trying to predict, I don't know, the exact weather on a specific day 10 years from now, while also guessing the price of oil and whether people will still like eating fish and chips.
That's a pretty good analogy. It highlights the immense challenge for policymakers who need reliable long-term projections.
So what's the way forward then? Given all this uncertainty, how does the framework help?
Well, the framework itself provides guidance. It helps researchers identify and focus on the areas where uncertainty is highest.
Like where we have the least data or understanding.
Precisely. Take the Bering Sea pollock example again.
Mm-hmm.
Most of the historical data used in that analysis came from relatively cold years.
Okay.
We have very few observations, maybe none, of what happens in consistently warm years, especially if fish abundance is also low in those warm years.
So any predictions for that kind of future scenario, warm, low abundance, are basically out of sample. We're extrapolating way beyond what we've actually seen.
Exactly. And that means those predictions carry significantly greater uncertainty. The framework directs attention there. We need more research, maybe different modeling approaches, for those plausible but poorly observed future states.
Which implies that generic one-size-fits-all models probably aren't the answer.
Definitely not. Researchers need to roll up their sleeves and examine the specific unique details of each fishery.
What kind of details?
The local ocean currents and dynamics, the exact management rules in place, the types of vessels being used, the specific market demands, all of it. You have to figure out which mechanisms, economic and biological, are the most important drivers for that specific fishery.
And ultimately, where should the research focus be heading?
The paper suggests a pivot. We need to move beyond just describing the likely, often negative impacts of climate change
Towards solutions.
towards designing management systems that are inherently resilient to change. We need to build institutions, rules, and incentives that give harvesters the flexibility to adapt effectively as the ecosystem shifts around them.
So wrapping this up, the core takeaway from Haynie and Pfeiffer seems pretty clear.
I think so.
If you ignore the economics, profit motives, the costs, the constraints imposed by management rules, you're setting yourself up for some serious predictive failures.
Absolutely. And that means potentially unreliable, even damaging policy recommendations.
The framework they propose forces researchers, forces us, to consider the full, messy, complex reality of these social ecological systems. It pushes us past a simplistic biological view.
Towards a much more necessary and frankly more realistic economic understanding of how fisheries actually operate, especially under changing conditions.
It's about integrating the human dimension properly.
Which leads to a really important question, something for you, the listener, to think about. If we accept that harvester behavior, driven by economics and incentives, is perhaps the biggest source of uncertainty in how fisheries will respond to climate change, then how can global policy, how can management institutions move beyond simply reacting to changes after they happen? How can we proactively design systems that build in flexibility, that create the right incentives, ensuring that fishing communities can remain resilient and adapt, regardless of exactly where the fish end up moving in the future?
That's a really profound challenge to consider, how to build proactive resilience into the system itself. Excellent food for thought. Thank you for diving deep with us today.